Take a glass, hold it in your hand, now drop it. It shatters, pieces everywhere. The glass is destroyed, right? Gone, broken, no longer a glass. Wrong. That glass isn't destroyed, not even slightly. Every atom that was in that glass is still in the universe. The silicon dioxide molecules, the sodium, the calcium, they're all still there. They're just arranged differently now. What you call destruction is just rearrangement. And here's the thing that should completely change how you see the world. This isn't just true for glass. It's true for everything. You cannot destroy anything, ever. Not matter, not energy, not information. The universe doesn't allow it. There are laws, fundamental laws built into the fabric of reality that prevent destruction from ever happening. Let me show you what I mean. Start with something simple, mass and energy. In the 1700s, chemists noticed something strange. When they burned things, when they mixed chemicals, when they did reactions in sealed containers, the total mass never changed. You could turn wood into ash and smoke, but if you captured all the smoke, weighed everything together, the mass was exactly the same as before. This became the law of conservation of mass. Mass cannot be created or destroyed, only rearranged. Then in the early 1900s, Einstein showed that mass and energy are the same thing. E equals mc squared. Mass is frozen energy. Energy is liberated mass. They're interconvertible, and what's conserved isn't mass alone or energy alone, but the total mass energy of a system. So when you burn paper, you're not destroying it. The carbon in the paper combines with oxygen in the air. Chemical bonds break and form. Energy is released as heat and light. The atoms rearrange into carbon dioxide and water vapor. But every atom that was in that paper is still in the universe. Every joule of energy is still in the universe. Nothing is destroyed. Everything is conserved. This is absolute. This is foundational. In every experiment, ever made, mass energy is conserved. The universe keeps perfect accounts. Nothing gets lost. But wait, you're thinking, okay, fine, the atoms are still there, but the glass is destroyed, the paper is destroyed, the structure, the organization, that's gone. And that's what destruction means, right? Destroying the pattern, the arrangement, the function. Fair point. And this is where things get interesting. Because yes, when you break a glass, you destroy its structure. You increase disorder. The neat crystalline arrangement of atoms becomes a scattered mess of fragments. And this disorder, this chaos, this has a name in physics: entropy. Entropy is a measure of disorder, of randomness, of how spread out and mixed up things are. Then there's a law, the second law of thermodynamics, that says entropy always increases. In any closed system, things always become more disordered over time. Heat flows from hot to cold. Gases expand to fill containers. Structures break down. Entropy goes up. So yes, when you shatter a glass, you increase entropy. You destroy the pattern. But here's what you need to understand. That increase in entropy, that spreading of disorder, is itself a form of information. The universe doesn't forget what happened. The broken pieces carry the history of the breaking. Think about it. If you could track every atom, every photon, every quantum of energy, you could, in principle, reconstruct what happened. You could trace the trajectories back, figure out how the glass fell, where it hit, how it shattered. The information about the glass's past is encoded in the present state of all those fragments and scattered atoms. Nothing is erased. The universe remembers. Now you might say, okay, the information exists, but it's scrambled. It's useless. I can't unbreak the glass. The past state is gone in any practical sense. And you're right. This is the arrow of time. This is why we experience time as flowing in one direction. Entropy increases. Disorder spreads. Broken things don't spontaneously reassemble. We remember the past, but not the future. But, and keep this in mind because we'll return to it, the arrow of time is statistical, not fundamental. The laws of physics at the microscopic level don't distinguish between past and future. If you filmed individual atoms colliding and played the film backward, you couldn't tell. The interactions work the same both ways. The reason glasses don't unbreak is probability. There are vastly more ways for glass to be broken than to be intact. So systems naturally evolve toward more probable states, which means higher entropy states. The arrow of time emerges from statistics, from the overwhelming likelihood that disorder increases. But at the fundamental level, the laws are reversible. And that means, in a deep sense, the past isn't gone. It's still encoded in the present. All the information about how the glass was is preserved in how the universe is now. Let's go deeper. Quantum mechanics. At the quantum level, systems are described by wave functions, mathematical objects that contain all possible information about a particle or system. And there's a principle called unitarity that says the evolution of a quantum system is reversible. Information is conserved. If you know the wave function now, you can calculate what it was in the past and what it will be in the future. Nothing is lost. Every interaction, every measurement, every change in the system is encoded in the wave function's evolution. This sounds abstract, but it has real consequences. Take black holes. For decades, physicists worried about the black hole information paradox. The paradox goes like this: when matter falls into a black hole, it seems to disappear. The black hole has only three properties: mass, charge, and spin. Everything else about the infalling matter, its composition, its history, all that information seems to be lost. But quantum mechanics says information can't be lost. So where does it go? Stephen Hawking discovered that black holes emit radiation, now called Hawking radiation. As they radiate, they lose mass and eventually evaporate completely. But the radiation seemed to be thermal, random, carrying no information about what fell in. The information appeared to be destroyed. This created a crisis. Either quantum mechanics is wrong and information can be destroyed, or general relativity is wrong and something else is happening with black holes. The resolution, which is still being worked out, involves something called the holographic principle. The idea is that all the information about what falls into a black hole is encoded on its surface, on the event horizon. And as the black hole evaporates, that information is released in subtle correlations in the Hawking radiation. The details are complex and not fully understood. But the key point is this: physicists are confident that information is not destroyed even by black holes. The universe preserves information, always. It's a fundamental principle. So let's step back. What have we learned? You can't destroy matter or energy. Conservation laws prevent it. Every atom, every joule, every quantum of anything is still in the universe. You can't destroy structure in a way that erases history. When you break something, you increase entropy, but the information about what happened is preserved in the configuration of all the resulting pieces and particles. You can't destroy quantum information. The wave function evolves unitarily. Every state contains the seeds of past states and future states. The universe is a system with perfect memory. Nothing is ever truly lost. Now, why does this matter? Why should you care? First, it changes how you think about permanence. We think of destruction as final. When something is destroyed, it's gone. But it's not. It's transformed. The atoms are still there. The energy is still there. The information is still there. The information is still there. What we call destruction is just rearrangement on a scale we notice. Second, it reveals something deep about the nature of physical law. The universe operates according to rules, and those rules are conservative. They preserve quantities. They maintain balance. The universe is not chaotic and arbitrary. It's structured and lawful in ways that prevent true loss. Third, it connects to some of the deepest questions in physics. Why is information conserved? What does it mean for the past to be encoded in the present? How does the arrow of time emerge from time-symmetric laws? These are active areas of research. We don't have all the answers. But the fact that we can ask these questions, that we can trace their implications, that we can test predictions and find that information really is preserved, that's extraordinary. Let me make this concrete with everyday examples. You burn a log, the log is destroyed, right? No. The carbon in the wood combines with oxygen. Carbon dioxide is released. Water vapor is released. Heat and light are radiated away. Ash remains, which is mostly minerals that didn't combust. Every atom from the log is accounted for. They're just in different molecules now, scattered into the air, absorbed into the ground, radiated as energy into space. The log structure is gone, but the log substance is entirely conserved. You delete a file on your computer. The data is destroyed, right? No. When you delete a file, the computer just marks that section of the hard drive as available for overwriting. The data is still there until something else writes over it. And even if you overwrite it, even if you physically destroy the hard drive, the information was briefly encoded in electromagnetic fields, in the heat generated, in the precise trajectories of electrons. In principle, if you could track everything, the information could be reconstructed. You eat food. The food is destroyed in your digestive system, right? No. The food is broken down into molecules. Those molecules are absorbed. Some are used for energy. Some are used to build your cells. Some are excreted as waste. But every atom that was in that food is still in the universe. Nothing is destroyed. It's rearranged, metabolized, integrated into your body, or expelled, but conserved. This has philosophical implications. If nothing can be truly destroyed, if the universe preserves all information, then in some sense, everything that has ever happened is still part of the universe, not as a recoverable memory, not as something you can access, but as information encoded in the structure of reality. The past is not gone, it's compressed, scrambled, spread across the universe in the positions and states of particles, in the correlations between quantum systems, in the patterns of radiation traveling through space. And the future, in a deterministic or at least highly constrained sense, is already implicit in the present. The wave function contains it. The conservation laws constrain it. This is not mysticism. This is physics. When physicists write down the equations describing the universe, they include all of time. The laws are time symmetric or nearly so. The universe is a four-dimensional structure, and everything that happens is part of that structure. You can't destroy your past. It's woven into who you are. Every experience, every choice, every moment has left traces in your brain, in your body, in the world around you. Those traces are physical. They're encoded in neural connections, in scars, in memories, in the positions of atoms. You can't destroy your mistakes. You can't erase your regrets. But you also can't destroy your achievements, your moments of joy, the good you've done. It's all still there, encoded in the structure of reality, contributing to the present and the future. The universe is meticulous. It keeps perfect records, not in the sense of a cosmic ledger you can consult, but in the sense that every event leaves traces, and those traces are preserved in the subsequent state of the universe. This is what conservation laws mean. This is what the preservation of information means. The universe doesn't forget. It can't. The laws of physics prevent it. Now there are nuances. In classical mechanics, you can in principle reverse any process. In thermodynamics, entropy increases, so processes are irreversible in practice, but not in principle. In quantum mechanics, measurement seems to introduce irreversibility, but the underlying wave function evolution is unitary and reversible. In general relativity, the expansion of the universe and the formation of black holes raise questions about information preservation, but the current best understanding is that information is still conserved. These nuances are important. Physicists are still working them out, but the overarching principle holds. Information is not destroyed. Let me give you a thought experiment. Imagine you could track every particle in the universe, every atom, every photon, every quantum field excitation, and imagine you knew the laws of physics perfectly. Could you reconstruct the past? And principle, yes. If you know the present state completely and you know the laws, you can run the equations backward. You can calculate where every particle was at any previous time. The information is all there. It's just incredibly scrambled. In practice, this is impossible. The number of particles is astronomical. The calculations are beyond any conceivable computer. Quantum uncertainty adds complications. But the point is, the information exists. The past is encoded in the present. This is not science fiction. This is what the laws of physics tell us. The universe is reversible at the fundamental level. What seems like destruction, what seems like loss, is just rearrangement. The universe shuffles the deck, but it doesn't lose any cards. Now, let's connect this back to where we started. You drop a glass. It shatters. You thought you destroyed it, but you didn't. You rearranged it. The atoms are still there. The energy that broke the bonds was conserved. The sound waves that radiated out carried energy into the air. The heat generated was dissipated. Everything is accounted for. And more than that, the information about how the glass broke is preserved. In the pattern of the cracks, in the distribution of the fragments, in the exact trajectories of every shard. If you had perfect knowledge and infinite computing power, you could reconstruct the entire event. You could figure out the height from which the glass fell, the angle at which it hit, the internal stresses in the glass before it broke. The past is not gone. It's encoded in the present. The universe remembers. So what can you destroy? You can destroy patterns. You can destroy structures. You can destroy functions. You can increase entropy. You can make it very, very difficult to recover information in practice. But you cannot destroy the fundamental constituents of reality. You cannot destroy matter energy. You cannot destroy matter energy. You cannot destroy information in the quantum mechanical sense. You cannot erase the past from the universe. The universe is conservative. It preserves. It remembers. And this is built into the deepest laws we know. Why don't we notice this in everyday life? Why does destruction seem so final, so complete? Because we're not tracking atoms. We're not calculating wave functions. We're experiencing the world at a macroscopic level, where entropy matters, where disorder spreads, where practical irreversibility dominates. When you burn a book, the words are destroyed in any meaningful sense. You can't read them anymore. The information encoded in the arrangement of ink on paper is lost to you, but the atoms are still there. And in an abstract sense, the information about what was written is still encoded somewhere in the universe, in the correlations between all the particles produced by the burning. We don't notice conservation because our timescales are short, our measurements are coarse, and our perspective is limited. We see the broken glass, not the preserved atoms. We see the burned paper, not the conserved energy. But the conservation is real. It's been tested. It's fundamental. There's something beautiful about this. The universe doesn't lose things. It doesn't forget. It's not wasteful. Every bit of matter, every quantum of energy, every piece of information is part of an ongoing story. Nothing is discarded. Nothing is erased. You are made of atoms that were forged in stars billions of years ago. Those stars exploded, scattering their contents across space. The atoms drifted, eventually coalescing into the solar system, the Earth, the biosphere, and eventually you. Those atoms carry that history. They've been part of countless other structures before you. Rocks, oceans, plants, animals, other humans. And after you, they'll be part of other structures. They'll return to the Earth, be absorbed by other organisms, eventually perhaps return to space, but they'll never be destroyed. They'll never cease to exist. They'll just keep rearranging, keep participating in the ongoing process of the universe organizing and reorganizing itself. So here's the final point. The next time you break something, burn something, delete something, remember, you're not destroying it, you're transforming it, you're rearranging it, you're increasing entropy. But the fundamental stuff of reality, the atoms, the energy, the information, that's all still there. The universe is conservative, it preserves, it remembers. And once you see this, once you really understand it, you realize that destruction is an illusion. A useful illusion for navigating everyday life, but an illusion nonetheless. What's real is transformation. What's real is rearrangement. What's real is the endless dance of matter and energy, following laws that ensure nothing is ever truly lost. The glass isn't destroyed. It's liberated into a new configuration. The paper isn't destroyed. It's transformed into gas and energy and ash. Nothing is destroyed. Everything is conserved. And that's not philosophy. That's not poetry. That's physics. That's the universe as it actually is. Strange, beautiful, and more carefully organized than we ever imagined. That's the truth about destruction. Not comfort, not simplicity. Truth.